Something changed in the atmosphere above the Arctic during the last week of January. Not a storm, not a sudden plunge, just a gradual rearrangement of air that didn't follow the pattern forecasters had been tracking since December. The models predicted one thing. The measurements showed another. For a few days, it didn't seem urgent. Then weather stations across northern Canada began reporting pressure readings they hadn't seen in nearly 40 years. The numbers themselves weren't dramatic. What caught attention was the speed at which they were shifting and the direction they were moving. When the European Centre for Medium-Range Weather Forecasts issued its revised outlook for mid-February, the language stayed measured, professional. But the temperature projections for North America and Europe had been quietly adjusted downward, not by a small margin. By the first week of February, the question meteorologists were asking each other wasn't whether an unusual freeze was approaching. It was whether the atmospheric system driving it had already passed the point where normal recovery patterns would apply. That question didn't have a clear answer. It still doesn't. If you're here because you value calm, scientifically grounded explanations of rare atmospheric events, the kind of content that helps you understand what's actually happening rather than reacting to headlines, this video will walk you through what makes this freeze different from anything we've prepared for. Like and subscribe if this approach feels useful. Turn on notifications if you want clarity as this develops. Let's begin. Winter in the mid-latitudes follows a rhythm. Cold air builds over the polar regions during the darkest months. It pools, it deepens. Then, as the jet stream meanders, portions of that cold break away and slide southward, bringing snow to Chicago, freezing rain to London, sub-zero nights to Toronto. These southward surges happen every year. They're expected. Meteorologists track them weeks in advance, watching the upper-level winds for the telltale waviness that precedes a cold outbreak. The air arrives, lingers for a few days, then retreats as warmer systems push back from the south and west. By mid-February, even in harsh winters, the pattern begins to weaken. Daylight increases. Solar heating becomes more effective. The polar reservoir starts to lose its grip. That's the normal cycle. What began unfolding in late January didn't follow it. The first indication came not from temperature records, but from something more subtle, the shape of the cold air mass itself. Meteorologists reviewing upper atmosphere data noticed that the boundary between Arctic air and mid-latitude air wasn't behaving like a typical front. It wasn't advancing and retreating in pulses, it was settling, locking into place across a latitude band from roughly 35 degrees to 55 degrees north. This wasn't movement, it was occupation. By February 1st, the 500 millibar height charts, maps showing atmospheric pressure at roughly 18,000 feet above sea level, revealed something forecasters recognized but rarely saw this pronounced, a blocking pattern stretching from the North Atlantic across Greenland and into central Canada. High-pressure ridges had formed in positions that effectively prevented the usual west-to-east flow of weather systems. The atmosphere, in essence, had stopped its normal circulation. When atmospheric flow stalls like this, cold air can't be flushed away by incoming warmer systems. It accumulates, deepens, and because it's no longer being mixed with milder air from the south, it becomes progressively colder at the surface. Not through any dramatic influx of new Arctic air, but simply through radiative cooling under clear skies. The models predicted this blocking pattern would last 3 to 5 days. It lasted 9, then something unexpected happened. Instead of breaking down as the model suggested, the block reorganized. The high-pressure ridge over Greenland intensified. A second ridge formed over Scandinavia. Between them, a corridor of northerly flow opened. Not the chaotic, turbulent winds of a typical cold snap, but a steady laminar stream of air moving directly from the Arctic Ocean towards Central Europe and Eastern North America. Meteorologists have a term for this configuration, a split flow regime. It's not rare, but its persistence is. What made this particular pattern unsettling wasn't its structure, it was its timing. By the second week of February, the Arctic itself should have been losing its coldest air to mixing and solar heating. Days are lengthening rapidly at high latitudes this time of year. The sun angle, while still low, is no longer negligible. Under normal conditions, the polar vortex, the large-scale circulation of air around the North Pole, begins to weaken as stratospheric temperatures start their seasonal rise. This year, that weakening didn't occur on schedule. Temperature readings from weather balloons launched across northern Canada and Siberia in early February showed that the layer of atmosphere between 10 and 30 kilometers altitude, so the lower stratosphere, remained unusually cold. Not record cold, just persistently cold. Cold enough to maintain the strong temperature gradient that keeps the polar vortex tightly wound. And a tightly wound polar vortex means the reservoir of cold air over the Arctic stays coherent, concentrated, available for transport. The forecast models, designed around climatological averages, expected the vortex to loosen by now. They expected the blocking pattern to erode. They expected February to behave like February. Instead, the atmosphere was behaving like late December. On February 7th, a research meteorologist at Environment Canada published a brief technical note on a professional forum used by forecasters. The note wasn't alarmist. It simply pointed out that the current atmospheric configuration had no close analogue in the reanalysis datasets going back to 1979. Not unprecedented, not historic, just no close analogue. The note included a single chart comparing the current 500 millibar pattern with the 20 coldest February periods on record across North America. In every previous case, the blocking pattern had been either weaker, shorter-lived, or positioned differently, usually centred over Alaska or the Canadian archipelago, not Greenland. The current block was both stronger and located further east. That subtle difference in position changed everything. A block over Alaska directs cold air into western North America, but allows the Atlantic storm track to remain active, bringing periodic warm intrusions to the east coast and Europe. A block over Greenland shuts down both pathways. It creates an atmospheric dam that holds cold air in place over the entire northern tier of the mid-latitudes. No relief from the west. No moderation from maritime air. Just stagnation. By February 8th, meteorologists weren't debating whether a significant cold event was coming. They were debating whether the term cold snap even applied to what the models were now showing for the period after February 10th. A cold snap implies brevity, a temporary departure from normal that will self-correct within days. What the atmosphere was constructing looked more like a regime change. One forecaster, reviewing the extended range ensemble guidance late on February 8th, noted in an internal email that the model spread, the range of possible outcomes, had collapsed. Usually when models look 2 weeks ahead, they show wide disagreement. Some runs predict cold, others mild, most something in between. For the February 10th 25 period, nearly every ensemble member showed the same thing: persistent, stationary cold across the northern mid-latitudes, with no clear mechanism for breakdown. When models agree that far in advance, they're usually right about the pattern. They're often wrong about the intensity. The question wasn't whether the freeze would happen, it was whether we understood what kind of freeze it would be. When severe cold reaches the mid-latitudes, news reports tend to use one of two phrases: polar vortex collapse or stratospheric warming event. The terms sound technical, authoritative. They suggest meteorologists understand exactly what's happening and why. Most of the time they do, but the language itself creates a problem, one that becomes significant when the atmospheric behavior doesn't quite match the textbook definitions. The polar vortex isn't a single coherent entity. It's not a storm system that can break apart and send fragments southward, despite how it's often visualized in media graphics. The term actually refers to a pattern of circulation, a ring of strong westerly winds that forms each winter in the stratosphere, roughly 10 to 50 kilometers above the Earth's surface. When those winds are strong and tightly organized, they act as a containment system. Cold air stays locked over the polar regions. When the winds weaken or become disrupted, the containment fails. Cold air can then spill southward into regions that don't normally experience it. That's the simplified version. The reality is more complicated. A true polar vortex disruption begins in the stratosphere, where sudden warming events can cause the circumpolar winds to slow dramatically, or even reverse direction. These stratospheric disturbances can then propagate downward over a period of weeks, eventually influencing the troposphere, the lower 10 kilometers of atmosphere where weather actually occurs. The key word is can. Not all stratospheric disruptions make it to the surface. Many dissipate before they influence ground-level weather. And, conversely, severe cold outbreaks can occur without any stratospheric warming event at all, driven instead by tropospheric blocking patterns, sea ice configurations, or snow cover feedbacks that have nothing to do with the stratosphere. The February 2025 event fell into an uncomfortable category. There was stratospheric activity. Temperature readings from the lower stratosphere showed a warming pulse in late January, modest by historical standards, but present. The polar vortex did weaken slightly. By early February, wind speeds at the 10 millibar level, roughly 30 kilometers altitude, had dropped to about 60% of their mid-January values. Under normal circumstances, that degree of weakening would be noted by researchers, tracked for a few weeks, then filed away as a minor event if it didn't propagate downward. This time, it did propagate. But not in the way the coupling mechanisms usually work. Typically, when stratospheric warming influences surface weather, the effect appears 2 to 4 weeks after the initial warming. The downward progression is gradual. The stratospheric disturbance destabilizes the upper troposphere first, then works its way toward the surface over successive days, allowing forecasters to watch the evolution and adjust predictions accordingly. In early February, that timeline compressed. The stratospheric warming pulse began around January 26th. By February 4th, only 9 days later, tropospheric circulation patterns across the North Atlantic and North America had already shifted into configurations consistent with a mature vortex disruption. Something accelerated the coupling. Meteorologists reviewing the data couldn't immediately identify what. The warming event itself wasn't exceptional. The vortex weakening was moderate. There was no obvious tropospheric precursor, no unusual blocking pattern already in place that the stratospheric signal could amplify. Yet the surface response was rapid and pronounced. On February 6th, a team of researchers at the Karlsruhe Institute of Technology published a preliminary analysis on a preprint server. The paper didn't offer conclusions. It simply documented the timeline and noted that the observed coupling speed fell outside the range of variability seen in the 46 previous stratospheric warming events recorded since 1979. Not impossible, just unusually fast. The paper included a single sentence in its discussion section that several forecasters privately found more unsettling than any of the data. It remains unclear whether the stratospheric warming initiated the tropospheric response, or whether both were responding to a forcing mechanism not yet identified. That sentence implied something important. It suggested the possibility that the stratospheric event and the surface cold weren't cause and effect. They might both be symptoms of something else, some larger-scale reorganization of the atmospheric system that happened to express itself in both the stratosphere and troposphere simultaneously. If true, that would mean the usual framework for understanding polar vortex disruptions didn't fully apply here. And if the framework didn't apply, the standard recovery timeline didn't either. Polar vortex disruptions typically last 1 to 3 weeks at the surface. The cold air surges southward, persists for several days, then retreats as the vortex restabilizes and westerly flow resumes. There are exceptions. The February 2018 event over Europe lasted nearly 4 weeks, but even extended events show variability. Cold periods alternate with brief warm spells as weather systems continue to move through the affected regions. The February 2025 pattern wasn't showing that variability. Instead, the blocking configuration that had formed over Greenland and Scandinavia was reinforcing itself. High pressure remained locked in place. The jet stream, rather than undulating in its normal wave pattern, had effectively split into two branches. One flowing across southern Europe and the Mediterranean, the other across the North Atlantic far south of its usual position. Between those two branches, a zone of stagnant, progressively colder air. By February 8th, some meteorologists had quietly stopped referring to the event as a polar vortex collapse. In technical discussions, they'd begun using the more neutral term persistent negative NAO configuration, referring to the North Atlantic Oscillation, an index that measures the pressure difference between Iceland and the Azores. The shift in terminology wasn't semantic caution. It was an acknowledgement that the standard conceptual model, stratospheric disruption leads to temporary surface cold, wasn't capturing what was developing. This wasn't a disruption propagating downward from the stratosphere. This was a tropospheric pattern that had organized itself and wasn't showing any signs of the instability that usually causes blocking patterns to collapse. One university researcher, asked by a colleague whether this qualified as a vortex event, responded, "The vortex weakened. Cold air is moving south. By definition, yes. But if you're asking whether understanding the stratospheric component helps us predict what happens next, I don't think it does." The models that specialize in stratospheric-tropospheric coupling were performing poorly. Their forecast for mid-February kept shifting colder with each new run, suggesting they were underestimating the persistence of the surface pattern. Meanwhile, the purely tropospheric models, the ones that don't explicitly account for stratospheric processes, were performing only marginally better. Neither framework was quite right. On February 9th, the ECMWF issued an internal technical note to National Meteorological Services. The note acknowledged that forecast confidence for the February 10th 20 period was lower than typical for a 10-day outlook. Not because the models disagreed on the overall pattern to a year, they were remarkably consistent on that, but because the physical processes maintaining the pattern weren't clearly understood. The note used careful language. It didn't suggest the models were wrong. It suggested they might be right for reasons they weren't designed to capture. That distinction mattered. If the models were correctly forecasting persistent cold because they were accurately simulating atmospheric dynamics, then the forecast would likely hold. But if they were forecasting persistent cold as a statistical artifact, because the pattern happened to resemble other historical cases, then small changes in atmospheric configuration could produce outcomes the models weren't anticipating. Forecasters had no clear way to determine which scenario applied. By the evening of February 9th, the discussion among meteorologists had shifted away from terminology debates. Whether this was called a polar vortex event, a blocking pattern, or a negative NAO regime didn't change what was about to happen. Starting February 10th, a large portion of North America and Europe would experience sustained cold that the naming conventions and conceptual frameworks had been designed to explain, but in this case couldn't quite account for. The cold was coming regardless of what it was called. What remained uncertain was whether it would behave the way the categories predicted. January 28th, 2025 was unremarkable from a meteorological standpoint. The stratospheric warming event that had begun 2 days earlier was proceeding as expected. Models showed it would remain a minor event, interesting to researchers tracking polar dynamics, but unlikely to produce significant surface impacts. The polar vortex was weakening, yes, but not collapsing. The projection was for a modest southward excursion of cold air into central Canada by early February, followed by a return to seasonal norms. Forecasters at the Canadian Meteorological Centre reviewed the morning data and found nothing that contradicted that outlook. By the morning of January 30th, that outlook was obsolete. What happened in the intervening 48 hours wasn't captured by real-time monitoring systems. There was no sudden dramatic shift visible on satellite loops, no abrupt pressure crashes recorded by surface stations. The change occurred gradually enough that individual 6-hour analysis cycles showed nothing alarming. But when meteorologists compared the atmospheric state on January 28th to the state on January 30th, they were looking at a fundamentally different configuration. The first person to notice was a graduate student at McGill University. She was working on a research project examining sea level pressure gradients across the North Atlantic and had written a script to automatically flag unusual changes in the gradient field between successive analysis times. The script was designed to catch data errors, instances where measurement glitches created unrealistic jumps in pressure values. On the morning of January 30th, the script flagged 17 stations. At first, she assumed it was an instrumentation problem. 17 simultaneous failures would be unusual, but the alternative, that the pressure field had actually changed that much in 48 hours, seemed less plausible. She checked the raw observations. They were valid. She checked the quality control flags. No anomalies reported. She ran the comparison again using a different reanalysis dataset. Same result. The sea level pressure gradient between southern Greenland and Iceland, a region that largely determines how vigorously Atlantic storms track toward Europe, had intensified by 14 millibars over 48 hours, not in a single storm system which can produce localized pressure falls of that magnitude. Across the entire gradient field, the large-scale pressure pattern had reorganized. She mentioned the finding to her advisor, who initially suggested it might be an artifact of the reanalysis interpolation scheme. Reanalysis products combine observations with model output to create a gridded picture of the atmosphere, and sometimes that process can smooth over rapid changes in ways that make them appear more dramatic than they were. But when they examined the raw station data, direct observations from weather buoys, ships, and coastal stations, the change was there, measured, documented in the hourly reports that National Weather Services archive, Between midday on January 28th and midday on January 30th, the pressure over southeastern Greenland had risen by 18 millibars. Simultaneously, pressure over Iceland and the Norwegian Sea had fallen by 8 millibars. That wasn't weather variability, that was structural change. High pressure building over Greenland is common in winter. It's part of the natural mode of atmospheric variability in the Arctic. What made this event different was the speed of development and the lack of any clear precursor. Blocking highs typically form gradually. A ridge amplifies over several days as upper-level winds slow and the flow becomes more meridional, oriented north-south rather than west-east. Forecasters can usually see these ridges building in the 5 to 7 day model guidance. This block appeared with less than 72 hours warning. On January 27th, the extended range models showed a weak ridge near Greenland that was forecast to remain transient, present for 2 or 3 days, then shifting eastward as the next Atlantic storm system approached. By January 30th, that transient ridge had intensified into a deep stationary high-pressure system with a central pressure exceeding 1040 millibars. The approaching Atlantic storm, rather than pushing the ridge aside, had split, one piece deflecting northward into the Arctic, the other diving southward toward the central Atlantic. The block had established dominance over the weather pattern. Meteorologists reviewing the model performance later noted that the forecast error wasn't in the position of the high pressure. The models had correctly predicted a ridge near Greenland. The error was in the persistence. The models thought it would last 60 hours. It was still there 10 days later. What caused the ridge to stabilize so quickly remains unclear. Several atmospheric ingredients were present. Anomalously extensive snow cover across eastern Canada and Scandinavia, which increased surface reflectivity and allowed for stronger radiative cooling. Sea surface temperatures in the North Atlantic that were slightly cooler than average, reducing the amount of heat and moisture available to feed passing storm systems, and the stratospheric warming event which may have contributed to the tropospheric ridge amplification through mechanisms that are still being studied. But none of those factors, individually or in combination, clearly explain the 48-hour intensification. Blocking patterns require energy to maintain themselves against the atmosphere's natural tendency toward westerly flow. That energy typically comes from the interaction between atmospheric waves and the underlying jet stream, a process that operates over timescales of several days. This block intensified faster than that process typically allows. On February 1st, a forecaster at the Icelandic Met Office sent a message to a colleague at ECMWF. The message was brief. "Are we sure the January 30th analysis is correct? The gradient change seems physically implausible." The response came back within an hour. "We thought the same." Ran validation checks. Everything passed. It's real. What made the January 28th, 30th window particularly significant wasn't just that the blocking pattern formed. It was that its formation coincided with another development that, in isolation, would have been unremarkable. During the same 48-hour period, the jet stream over eastern North America underwent a sharp southward displacement. Jet stream meanders are normal. The polar jet, the river of fast-moving air that separates cold polar air from warmer mid-latitude air, constantly shifts position, dipping south in some regions, bulging north in others. These shifts create the day-to-day weather variability that characterizes mid-latitude climates. But the southward shift that occurred between January 28th and 30th wasn't a typical meander. Weather balloon launches from stations across Quebec and Labrador measured the altitude of the jet stream core, the level where wind speeds are strongest, at around 9,000 meters on January 28th. By January 30th, that altitude had dropped to 7,500 meters, a 500-meter descent in 48 hours. That kind of vertical displacement indicates a fundamental change in the thermal structure of the atmosphere. The jet stream's altitude is controlled by the temperature contrast between air masses. When that contrast sharpens, when cold air becomes colder or warm air becomes warmer, the jet stream adjusts its position and intensity. In this case, the adjustment was being driven by rapid cooling in the layer of atmosphere just north of the jet. Surface temperatures across the Canadian Arctic weren't falling dramatically during this period. They were seasonally cold, but not record-breaking. The extreme cooling was occurring aloft, in the layer between 3,000 and 7,000 meters altitude, where radiative heat loss under clear skies was proceeding unimpeded by cloud cover or moisture. That cooling was a direct consequence of the high-pressure block that had just formed over Greenland. High-pressure systems create sinking air. Sinking air suppresses cloud formation. Without clouds, the atmosphere loses heat to space more efficiently. And in late January, with minimal solar input to offset that loss, the cooling can be rapid. The block over Greenland was essentially creating its own reinforcement mechanism. By establishing clear skies over the Arctic, it was accelerating the cooling of the air mass beneath it. That cooling was sharpening the temperature gradient along the southern edge of the cold air. The sharper gradient was strengthening and displacing the jet stream, and the displaced jet stream was steering storm systems away from the block, allowing it to persist. It was a feedback loop that once initiated had no obvious break. Forecasters watching the pattern develop during the first few days of February recognized the feedback mechanism. It's well documented in atmospheric science literature. What they didn't anticipate was how quickly it would amplify. Climate models that simulate blocking events typically show this kind of feedback taking 5 to 7 days to reach maturity. The January 28th, 30th event reached maturity in less than 3. On February 3rd, a research meteorologist at Environment Canada ran a diagnostic calculation to estimate how much radiative cooling was occurring in the atmospheric column over northern Quebec. The calculation used temperature profiles from weather balloon soundings and standard radiative transfer equations. The results showed a heat loss rate of approximately 3.5 degrees Celsius per day in the layer between 3 and 6 kilometers altitude. She ran the calculation again, assuming she'd made an error in the input data. Same result. For context, typical wintertime radiative cooling rates in that region are around 1.5 to 2 degrees per day. The observed rate was nearly double the climatological average. That accelerated cooling meant the cold air mass over Canada was intensifying faster than seasonal norms would predict. And because the blocking pattern was preventing that cold air from mixing with warmer air to the south, it was accumulating rather than dispersing. By February 5th, temperature soundings over northern Manitoba showed a layer of air at 850 millibars, roughly 1,500 meters altitude, with temperatures below minus 40 degrees Celsius. That's not unprecedented for late January or early February. What was unusual was the depth of the cold layer. Typically, extreme cold in the lower atmosphere is confined to a shallow layer near the surface, with temperatures moderating rapidly with altitude. In early February 2025, the cold extended through a much deeper vertical column. Weather balloons ascending through the atmosphere reported temperatures below minus 30 degrees Celsius, all the way up to 600 millibars, nearly 4,000 meters altitude, a deep reservoir of cold primed for transport. What the 48-hour window from January 28th to 30th had done was set the initial conditions for everything that followed. It established the blocking pattern. It initiated the radiative cooling feedback. It displaced the jet stream into a configuration that favoured southward transport of Arctic air. None of those individual components was extraordinary. Their simultaneity was. By February 9th, when meteorologists attempted to reconstruct the sequence of events that led to the mid-February forecast, they kept returning to that 48-hour period. Every subsequent development, the persistence of the Greenland block, the intensification of the cold pool over Canada, the split-flow jet configuration, could be traced back to the atmospheric state that had been established by January 30th. One forecaster, reviewing the timeline, made a note in a case study document that would later be circulated among colleagues. If the block had formed 500 kilometers further west, or if the jet stream displacement had occurred 2 days earlier, the pattern would likely have been transient. The timing and positioning were precise enough that the system locked into a stable configuration before any counteracting processes could disrupt it. The atmosphere had found an equilibrium that favoured cold, and once established, that equilibrium showed no inclination to break. Cold air is denser than warm air. This is fundamental. It's why cold air sinks, why Arctic outbreaks slide southward along the surface rather than riding above warmer air masses, why frost settles in valleys while hilltops remain milder. The relationship between temperature and density is one of the most reliable principles in atmospheric physics. For every degree Celsius the air cools, its density increases by approximately 0.37%. The math is straightforward. The behaviour is predictable. Until it isn't. On February 5th, a research team at the Danish Meteorological Institute was analysing upper air observations from weather balloons launched over eastern Greenland. They were studying the vertical structure of the blocking high, mapping how temperature and pressure varied with altitude to better understand why the block was proving so persistent. One of the researchers noticed something odd in the density calculations. At an altitude of approximately 3,000 meters, the air density was measuring 1.08 kilograms per cubic meter. Given the observed temperature of minus 38 degrees Celsius and the atmospheric pressure at